Assalamu alaikum dear students. In this video lesson I'm going to solve 2024-2025 preliminary exam questions. Just to let you know before we start, the original copy was released in Kurdish only. So this is not the original copy. What I have done is I've translated the Kurdish into English so that you benefit from this. Alright, if you're ready, let's begin. The first question that we have says, a point on the edge of the wheel travels an arc of length, or an arc length here. So we have basically an arc length, which is clearly delta S, and that is basically 5 meters. When it rotates through an angle of 1 over pi rev, what is the radius of the wheel? So clearly they're asking you to find the radius, while delta theta is given, and then the radius is unknown. So for the first question here, we can say the arc length is 5 meter. Delta theta, it is 1 over pi rev. But look, rev has to be, or needs to be converted. Each rev is 2 pi radian. Pi and pi cancel out. So we can say delta theta will be 2 radians here. Now find the radius. We know that delta theta, it is equal to arc length divided by the radius, as you know. So the radius, make it the subject, equal to arc length by delta theta. That is 5 divided by 2. That is clearly 2.5 meters, since it is the radius. And that is option B here. All right, moving to the next question here. What do we have? Okay, the second question here that we have says, a tire of a car is rotating with an average angular speed of 125 radians per second. So this is omega. That is the second question. So omega is 25 meter per second, radian per second, 25 radian per second. What is the time taken? So this is for that. What is the time taken for the tire to rotate 20 radian? So delta t is unknown. Delta theta is 20 radian. Now, since omega is given, we know that omega is equal to delta theta over delta t. The question is about the time, so delta t, it is delta theta over omega. You can see that this is basically radian per second, this is radian, so no conversion needed. In this case, we have 20 divided by 25. That is going to be, what is it going to be? Let's use a calculator. So we have 20 divided by 25. The answer is going to be 0.8. So we can say the time here is 0.8 seconds. So this is delta t. So do we have 0.8 seconds? Yes, and that is option D here. All right, moving to the next question here says, what do we have in here? That's the third question now. It says, a car is traveling at a speed of 30 meters per second. So this is, we can say, tangential, that is initial, of course. Let's just call it V initial. That is 30 meters per second. While braking, it experiences a negative acceleration. So acceleration is negative now, 2 meters per second squared. How many revolutions does each tire make? So delta theta is unknown, or find that, but in revs, don't forget. Does each tire make before coming to a complete stop? A complete stop, that means omega final is 0. Assume that none of the tires skid and that each tire has a radius of 0.3 meters. Now for this question, it can be solved in two different ways. First of all, these, let's say, a tangential or translational values can be converted to angular. Then we can find delta theta, and then we can, after that, we can convert the theta into revs. There's another method here. We could use these values as it is given. We can find delta x, but delta x is basically the same as arc length here. So we'll find delta theta, then after that we'll convert that into angular displacement. Then of course we'll find the number of revs in here. So you could try both. Let me just try this one here, since it might be easier for some of the students, by the way. So in this case, we'll say omega initial. How do we find omega initial? That is, of course, clearly equal to tangential over the radius. If I start from the beginning here, we know that tangential, it is equal to omega times the radius. If you want to find omega, it is equal to tangential over the radius. The tangential that we have, that is going to be initial, it is 30 divided by 0.3. So it is clearly equal to if we just multiply, let's say, so let's just call it this way, 300 divided by 3, if I just multiply both up and down by 10. So that is going to be 100 radian per second. By the way, use a calculator, you'll get this. Omega final, it is going to be 0 because tangential is 0. I should have wrote tangential here. Okay, and then what about the acceleration? We do the same thing. Angular acceleration equal to tangential over the radius, which is -2 divided by 0.3. So use a calculator. -2, you don't have to write the negative though, divided by 0.3, that is -6.6, you can say. And of course, this line here, it means it continues, so we can say 6.7 by rounding here. Now, all you have to do, just find angular or delta theta. But look, like out of the 4 equations of motion, which one of them will you use? Delta t, if you have noticed so far, delta t is neither given nor required, so we can use the 4th equation here. So the 4th equation is omega final squared, it is equal to omega initial squared plus 2 times angular acceleration delta theta. You'll have to find delta theta first. That is going to be in radian, then you can convert into revs. So final is 0, initial is 100, but that is going to be squared plus 2 times. The acceleration is -6.67 by rounding times delta theta here. So that is 0, it is equal to 10,000, right? We could say minus 2 times -6.67. Let's see what that equal to. 2 times, let's just put the negative aside, 6.67. That is going to be 13.34. 13, let's just remove this one, 13.34 delta theta. Now this is negative. If we take this one to the other side, of course, it's going to be positive. So we'll say positive 13.34 delta theta, it is equal to 10,000 radian per second. Now all you have to do, just find delta theta, which is equal to 10,000 divided by 13.34. Let's see what that equal to in radian. So we'll say 10,000 divided by 13.34. The answer is equal to 749.6. Of course, we can round it up to 750, but this is in radian, don't forget. The question says how many revs. Now, you know that in order to convert radian to rev, we could just simply divide by 2 pi. So we can say 749 point whatever, or you could go ahead and divide 750, the same thing, divided by 2 pi. Use a bracket. That is basically 2 pi. And then the answer is going to be 119.03. We could just say delta theta, it is equal to 119 revs. Do we have this in the answer? Let's go back to the 3rd question. Yes, and that is option C here. Can you see? Zoom out a bit. So 119.3 revs. So you can take away the 0.3. So we'll have 119 revs here. Okay. There is the second method, by the way. You can use these values that are given here. Let me just give you a tip how this can be used. We'll use the 4th equation again just to find delta x. Remember, delta x in that case, it is the same as the arc length here. So v final, it is squared, it is equal to v initial squared plus 2 tangential acceleration delta x. But instead of delta x, I can write the arc length in here. So you can find the arc length. Once you do that, delta theta, it is equal to arc length divided by the radius. You'll find the answer in radian. But then after that, it will divide by 2 pi to get the answer in revs, which, and most of the time for my students, I'll do this method because it has less steps here, but you have to be careful here so that you won't be confused here. Okay, that is basically for question 3. Now, as for question 4, what do we have? It says the time rate, let's zoom in, the time rate of change of the direction of the velocity. So whenever there is the time rate of change of the direction of velocity, this is clearly the definition of centripetal acceleration. So it is not angular velocity, angular acceleration, or tangential acceleration. You could think of this as the centripetal acceleration is change in the direction of the velocity divided by the time. That is centripetal acceleration. All right, now for question 5 here, says an object is moving in a circle at a constant speed. Now, I want you to be really careful here, and you can write this as a note or as a tip for yourself. Remember, whenever you see a circle, or whenever the word or an object is moving in a circle, immediately that means you must have centripetal acceleration. And of course, you cannot have acceleration if you don't have a centripetal force. That means whenever an object is moving in a circle, there's always centripetal acceleration and force. The second part says constant speed. Whenever it says constant speed, that means V initial is the same as V final, which means that the tangential acceleration is 0. If it is constant speed, that of course leads to a constant angular speed as well, which we can say omega initial is the same as omega final, and that is at this point, of course, it is equal, we can say the angular acceleration is 0. So let's analyze the option. It says, which of the following statement about it is motion is not true? So which one of these is not true? The first one says, it is centripetal acceleration is towards the center. So that is obvious, which is correct at this point, because you could draw a circle for yourself. Centripetal acceleration is always towards the center. So option A is correct. What about option B? The magnitude of the tangential speed is constant. That is also correct, because we said initial and final are equal here. C says the direction of the velocity doesn't change. Now, you really have to be careful here. So when we say velocity, that is basically both magnitude and direction. And when we say the direction doesn't change, and if that is not true for an object that is moving in a circle, because at some point, here's the direction. At some other time, you could say the direction would be this, in this direction. At some other times, for example, the direction is changing constantly here. So can we say the direction doesn't change? No. So this is incorrect. What about option D? A centripetal force acted on the object. That is also true. So the answer that we're looking for here is option C, which is incorrect. Now, the next thing that we have says, question number 6 says, the unit of universal gravitational constant is what? Well, this one is very easy, and you don't have to memorize anything. At least for this one here, as long as you know the equation. So the equation for gravitational force, let's say, Fg, that is equal to what? It is equal to G, that is constant for universal gravitation, m1, m2 over the distance squared. Now, all you have to do, make the this constant for universal, the subject, that is equal to force, or Fg times the distance squared divided by mass 1 times mass 2. Now, what are the unit of each one of these? Of course, the unit of force is Newton. The unit of distance, it is meter, but since it is squared, so meter squared over, mass is kilogram. So kilogram times kilogram, that is kilogram squared. Let's see if we have this one, and that is option D here. All right, so this would be correct. Now, question 7 says, how does increasing the length of a pedal arm on a penny farthing bicycle affects the amount of torque applied to the front wheel? So how increasing the length affects the torque, basically. So if you remember, this is, for example, the penny's farthing bicycle here, you could say. If this is the distance, that is a little bit. All right, so let's say this is the pedal arm. This is where you apply a force, and this is the distance here. So we know that torque, it is equal to force times the distance. So torque is directly proportional to the distance. So the bigger the distance, the bigger the torque. So if we increase the distance, of course, will the torque, like what happened to the torque? Will it increase? Yes, but let's check the other options. Does it decrease? No. Or does it decrease? No. Does it reduce to half? No, it doesn't change. That is also incorrect. So of course, option A is the correct answer here. Now, as for question 8 says, which of the following objects has a center of mass located at its geometric center? Now, how do we, all right, let's analyze the options here. So the question is about center of mass. The first thing says an ice cube. All right, so that is question 8. Remember, if we have an ice cube, let's draw a nicer cube here. So let's say this is a cube. Of course, you can see that the center of mass is right at the geometrical center. So ice cube is correct, but analyze or check other options. What about B? It says a uniform meter stick. Whenever it says meter stick, that means you have a stick, right, that is basically 1 meter long. So of course, if it is uniform, that means And like it is all the same. So in this case, of course, the center of mass, it is right at the center. So even for this one is correct. What about a donut, right? Well, all right, imagine this is a donut, for example. Now, you might say the center of this one is empty, but if you slice this one, let's say, to equal pieces, you would see that each one of these pieces, of course, would kind of like, or the center of each one of these, for example, let's say it is going to be right at the center here, even though it is empty space, where you can say it is a space, but in physics, for example, it is when we have something like this, when all these pieces, for example, can meet at one location. These are equal pieces here, so of course the center will be the center of mass in that case. So that is correct even for the donut. So in that case, of course, we can choose all of them. Okay. Now, question 9 here. All right, it says 2 girls weighing 450 and 300 Newton are sitting at the ends of a 2.5 meter board. Where along the board should the pivot be placed to achieve rotational equilibrium? Ignore the weight of the board. This makes it a little bit easier. All right, now take a look at this one here. All right. So what do we have in this case? I want you to focus. There is something, or you could say a tip. You need to know this one. It's not that difficult, but see how am I doing this one here. So for example, this is, first of all, this is what we have. Remember, we're in question 9 here. So there's basically a board. Let me move this one or zoom out a bit. You can have enough space. So there's basically, we can say a board, you can call it. Okay, so this board, or the length of this board, is basically 2.5 meters. That is the length of this one. 2 girls are sitting on this. One of them is 450 Newton. The other one is 300 Newton. Okay, now where along the board do we have to place the pivot so that we can achieve equilibrium? Now, you've learned by now that the pivot must always be closer to the person or to the object that weighs more in that case. So in that case, of course, it has to be closer to the 450. But look, none of the distances are given here. So we can call this one, if this is, we can call this one F1 and F2 here, and we can call this one D1 and then the other one D2. But how do we do that, guys? Now, let me take you back to this. In grade, let's say in math, you have this, for example. Let's say the length of this beam is 5 meters. And if we take a section off, let's call it X1, yeah? So what is the remaining distance here? Okay, so this is clearly X. What is the remaining distance here? We don't know the value for X, but can we say 5 minus X? Yes, that'll be for the other side. So if X is 1, then this side is going to be 5 minus 1, that is going to be 4. If X is 2, 5 minus 2 is going to be 3. So this is exactly what we're going to do here. We'll consider, or we'll call one side D here, right? So the other side, because the entire length is 2.5, so we'll say 2.5 minus D here. Okay, so that is basically what you need to do. Now, all you have to do, just apply the rotational equilibrium. We know that the net torque in that case is 0, which means that the torque that is counterclockwise must be equal to the torque that is clockwise. So for the counterclockwise, that is 450 multiplied by the distance is equal to, the other side we have 300 times, since we'll say 2.5 minus the distance. Okay, now one method you've learned, we could simply, for example, multiply this into the bracket, but there's another easier way. We could divide both sides by 300. All right, so this two, of course, cancel out. This side here is going to be 1.5D. Let me change the color back. Okay, so this side here, 1.5D. The other side is going to be just 2.5 minus D. Well, this is D, or distance, and distance has to go to the other side. So this is negative, go to the other side positive. So 1D plus, let's call it 1D plus 1.5D, that is 2.5. You agree, of course. 1 and 1.5, that is 2.5. D equal to 2.5. Divide the side by 2.5 or move this one under. So D equals to 1 meter. But careful here. Remember, where's D? Here is D. So now we can say this D is 1 meter. But 1 meter from who? Don't forget. That is 1 meter from the 450 Newton. What about the other side? The other side is going to be 2.5 minus 1. It is clearly equal to 1.5. But 1.5 from what force, or which girl? From the 300 Newton girl. Now we can check the options. The first one says, option A here says 1.5 meter from the 450. This is 450. So is it 1.5? No, it is 1. So this would be, option A is incorrect. Option B says 1 meter from the 450 Newton. That is correct. What about option C? 2.25 meter from that? No. 2 meter from the 300 meter girl? No. 300 Newton girl? No. So of course that is option B. I hope you understood how it is done. If not, you can always rewatch this or go back and then you rewatch this one until you fully understand this. Yeah. Let's clean this. All right. The next question that we have says, let's zoom it in again. In which of the following situations are both conditions of equilibrium, that is both translational and rotation, satisfied? So in this case, of course, there should be no rotation and no net force in that case. A bicycle wheel rolling along a level highway at a constant speed. Once again, we said if there's a constant speed, that means V initial is the same as V final. The tangential acceleration is 0, and it cannot be 0 unless if the net force is 0. And if that is the case, of course, omega initial is the same as omega final. Angular acceleration is 0. And if angular acceleration is 0, clearly the net torque must be 0 as well, we could say. All right, so of course this one is correct. What about B? The tire of a car slows down. As long as there is slowing down, that means V initial and final are not the same. And of course, there will be some torque as well. C says a bicycle parked against the curb. If it is parked, that means there's no motion. Clearly, there's no rotation. There's no rotation, so both A and C are correct. So we can choose option D. 11. Says a disc with a radius of 0.5 meter and a mass of 2.5 kilogram is rotating at an angular speed of 10 radian per second. What torque is required to bring the disc to a stop in 5 or 0.5 seconds? Now, you have to be able to see the keywords in here. All right, so what do we have here? Look, we have a radius that is obvious. We have the mass that is also clear. We have an angular speed. We can call this one initial. I'll tell you why in a second. What is the torque required? So you need to find the torque to bring the disc to a stop, which means to stop, that means omega final will be 0 in 0.5 seconds, and this is delta t. Okay, so let's do this. Now, because we have omega initial and final, and of course delta t, that means there is acceleration. And there is another keyword, as long as there's torque, you'll remember this, right? Newton's second motion of translational mass times acceleration. But here the question is about torque, so we can say torque, it is equal to, instead of mass, we have moment of inertia. Instead of acceleration, we have angular acceleration. So let's find each one at a time here. So starting with acceleration, that is question 11. Acceleration, it is equal to omega final minus omega initial divided by delta t. Well done. So final is 0 minus initial is 10 divided by 0.5. That is clearly negative 10 divided by 0.5. What is it equal to? That is equal to negative 20. You can use a calculator, by the way. If not, that is going to be negative 10 divided by 0.5. Multiply both up and down by 10. That would be 100 divided by 5. That is negative 100 divided by 5. That is basically negative 20. 20 what? Radian per second squared. That is the angular acceleration. Yeah. What about the moment of inertia? Well, moment of inertia is equal to 1 over 2. By the way, the equation is given, so you don't have to worry about it. Now it says a disk, so hopefully by now you know that the moment of inertia of a disk is 1 over 2 mass times the radius. All right, so the next thing that we have is times the mass, multiply by the mass, multiply by the radius squared. So 1 over 2, what is the mass? The mass is 2.5 kilogram times the radius is 0.5 squared. Use a calculator. We have 1 over 2, that is 0.5, multiplied by 2.5 kilogram, multiplied by 0.5 squared. The answer is going to be 0.3125. 0.3125. Now all you have to do, just plug this number back into the equations here. So now let's go back to the torque now. We can say 0.3125 times negative 20. So you do the math, of course, you'll find the answer, and let's do that. Multiplied by, we have this, negative 20. So the answer is going to be negative 6.25. Negative 6.25, that is Newton meter. So let's see if we have this in the options. That is option A here. Okay, now question 12 says what? A solid ball with a mass of 3.466 kilogram and a radius of 14 centimeters starts rolling from rest from a height of 3.5 meter down an incline. What is the ball's total kinetic energy when it reaches the bottom of the incline? Now, let me help you with these kind of questions. All right, whenever it says find the kinetic energy, or whenever you're required to find the rotational kinetic energy, I have a tip for you in that case. So let's say that is question 12. What do we have? There is an incline. There is a solid ball that is rolling from rest. So V initial is 0. And then the height is, the height of this incline is 3.5 meters. And then at the bottom here, once the ball reaches the bottom, find the total kinetic energy. We know that total kinetic energy, it is equal to, because there would be both rotational and translational, it is equal to translational kinetic energy plus rotational kinetic energy. Now, let me tell you about this. Whenever you have rotational kinetic energy, you can always write this instead. You can say C times translational kinetic energy. C times translational. But what is translational equal to? That is 1 over 2 mass times velocity squared. But what is C in this case? This is basically the factor that we multiply, let's say, the moment of inertia, which is basically for the shape. For example, for the ring is 1, for the disk is 1 over 2. Let's say for solid ball is 2 over 5. For thin spherical shell, it is 2 over 3, let's say. And of course, so forth in here. So, but remember, whenever you have rotational kinetic energy, you can write this instead. So going back to the total, here, we can say total kinetic energy, it is equal to translational kinetic energy plus C times, let's make C red in here, C times translational kinetic energy. Well, in this case, of course, we have translational kinetic energy here and there. We can take that as a common factor. It's going to be 1 plus C, okay? Now, so if I do this one more time, so let's bring 1 and C to the front, because that is a constant here. What is translational kinetic energy? That is 1 over 2 times the mass times the velocity squared. All right, but look, we don't have the velocity at the bottom of the incline. Well, can we find that? Absolutely, yes. So that is the first thing you need to know, right? This works, of course, with all these shapes that I have wrote their fractions or factors for. All right, now how do you find the velocity at the bottom of the incline? Once again, you don't have to memorize anything. All you have to do is just memorize this equation, and once again, it works with all the equations or those things that are rolling down here. So that is basically, we can say, V at the bottom tangential, that is 2 times GH, and then divided by 1 plus C. And I believe you know what is C by now. Okay, so let's find the velocity. 2 times 9.81. What is the height? 3.5 meters. And then 1 plus C. 2 over 5. Now all you have to do the math and then find the tangential. Okay, so let's do the math here. So that is, let me do the numbers first, and then we'll take the square root for that at the end. Okay, so first of all, we have 2 times 9.81, 9.81, and then multiply by 3.5, and that is equal to this much. We can divide that by, open a bracket, 1 plus, sorry, that is basically 2 over 5. You can add another or open another bracket. I can use this, of course, this button there, but I want to show you how you can do that because in the calculators you use, you don't have this option. That is 2 divided by 5 in here, close bracket for both. All right, and then you would do this, you will get 49.05. So that is basically 49.05. And if you take the radical for this, you'll get sort of, all right, so the radical of the answer, that is about 5.919. We can say 5.92 by rounding. 5.92, that is clearly, okay, let me just recheck. That is clearly 5. Okay. Let me do the math one more time. All right, 2 times 9.81 times 3.5, which is equal to 68 point. Let me just do this one here, like each one of these numbers alone. 68.67. For the bottom part here, we have 2 over 5. That is clearly 2 over 5 plus 1. That is 7 over 5, which is 1.4. So if we divide this two together, 68.67 divided by 1.4, the answer is going to be 49 point this much. And of course, if you take the radical for this, for the answer, it is equal to, this time it is equal to what? It is equal to about 7 here. So it was incorrect, the first one. So this is 7, we can say meter per second. 7 meter per second. All right, 7 meter per second. All right, now you know that, for example, this is the velocity. So go and put this velocity in, or plug this velocity into the equation here. So now, of course, we have 1 plus c, which is 2 over 5 times 1 over 2 times the mass. What was the mass of the solid ball? That is 3.466. 3.466 multiplied by 7 squared. Okay. Multiply by 7 squared. Let's do the math for this one too. I'll do the bracket first. 2 divided by 5, then plus 1, so 1.4 times the times 1 over 2, which is 0.5, times the mass, which is 3.466, times the velocity, 7 squared. So the answer is 118.8. 118.8. And of course, by rounding, we can say 119. So we can say the total kinetic energy, it is 119 joules. Do we have this? Yes, and that is option B here. I hope you understood this. So what have we learned in this? Remember, whenever you have rotational kinetic energy, you can always say C times the translational kinetic energy, and C is equal to this constant or these constant depending on the shape. And then as for whenever an object is rolling down, to find the velocity at the bottom of the incline, you can always use this equation. 2 times gh divided by 1 plus c. G is gravitational free fall acceleration, and then h is the height, 1 is basically just a constant factor, plus c, again, it is the constant or the factor that we multiply by the moment of inertia, and that depends on the shape. All right, moving next. We have question 13 here. So, okay, it says a mass spring system vibrating with a simple harmonic motion on a smooth horizontal surface. In what form is the energy in the system when the mass is at maximum displacement? Remember, it tells you a smooth horizontal surface. So here is the mass, let's say. At the maximum displacement here, of course, there is a spring stretch, so there is elastic potential energy. So the energy of the system, because there's no motion here, it is elastic potential energy. Is it gravitational? No. Is it kinetic energy? No, because it's not moving yet, or it's not released here, so it cannot be D as well. Now, as for question 14 says, which equation correctly describes the condition for observing the first dark fringe in an interference? So there are basically dark fringe, so that is a destructive interference. The equation for destructive interference, you know that, d sine theta is equal to 1 over 2 plus m or m, basically. It is always one less, we can say, than the number of the fringe here. So it says first dark, that means m is basically 0, because you always say m minus 1 in that case. So first dark, first minus 1, you could say that is going to be 0 here. So in this case, of course, what is left in the equation? D sine theta, that is equal to 1 over 2 lambda here, right? That'll be the condition for the first star. Do we have this? Yes, that is option A. All right, question 15 here says, what happens to the period of a vibrating mass spring system when it is transferred from Earth to the moon? Now, these questions can be misleading for a lot of students. Okay, so how do we know or whether if it is affecting or not? Look, first of all, whenever you have a question like this, whether if it is mass spring system or a pendulum, always write the equation for their period. That is, for a pendulum, for a mass spring system, it is 2 pi mass over spring constant, don't forget. So you can see here, the question says transferred from the Earth to the moon, the gravity changes there. But look, we have no gravitational acceleration in this equation. So we can say by changing the location here, the period will not be affected. So is it like, does it increase? No. Decrease? No. Increase by this factor? No. It does not change. Okay. Question 16 says, a tuning fork produces a sound with a frequency, so we have frequency, and a wavelength, lambda. What is the speed of a sound produced by the tuning fork? So v, using the equation of speed of sound, velocity, speed of sound, it is equal to frequency times the wavelength. The frequency is 230 hertz, multiplied by the wavelength, which is 1.5. So once you do this, of course, you will get 345 meter per second. That is the speed of sound. Do we have this? Yes, that is option B. Question 17 says, the waves are reaching a fixed boundary R. So there are two boundaries, or two types of boundaries. We have a fixed boundary, and we have a free boundary here. So once a wave, for example, going towards a fixed boundary, this wave, of course, it is going to be reflected and also inverted as well. So this is for a fixed boundary. But if it is free boundary, the wave is going towards the, let's say, the boundary here, and then after that, of course, it is going to be reflected, but it is not going to be inverted. So here we have a fixed boundary. So if it is fixed boundary, the first option says neither reflect nor reflected nor inverted, incorrect. Reflected but not inverted, incorrect. Reflected and inverted, it is correct. Inverted but not reflected, incorrect. So it is option C. Question 18 says, which of the following wavelengths will produce standing waves on a string that is 3 meters long? Now, remember this, there is also this equation we've studied in chapter 3 here. We can say the wavelength that is equal to what? It is equal to 2 times the length of a string, and then divided by, you can say A, you can consider this as the number of antinodi, you can call it the number of harmonics, makes no difference at this point. So if this is a string, for example, now, of course, if we have a complete, or you can say a full number of antinodes, that means there is a standing waves here. And if we don't have, or if we don't get a full, complete, a whole number of antinode, that means the wavelength will not produce a standing wave. So in order to do this, since we have different amplitudes, we can say 2L divided by the number of the wavelength here. Again, if we get a whole number, that means it is a standing wave. No whole number, no standing wave. So let's start with option A here. 2 times the length of the string is 3. Okay, and then divided by the wavelength, so that is going to be 6. Divided by the wavelength. The first wavelength that we have is 2. So 6 divided by 2, that is clearly 3. 3 what? We can say 3 antinodes. So if you have a full number of antinodes, that means, of course, we have a standing wave. This 1, 2, and 3. So this one forms a standing wave here. So option A is correct. Let's check the other options here. What about option B? It says 3.5. Well, 6 divided by 3.5, that is 1 point something. 6 divided by 3.5, that is 1.7. Is that a whole number? No. So B will not produce a standing wave. What about option C? Option C says 5 meters. Well, 6 divided by 5, that is not a whole number. You know that, okay? So it is basically 1 point something. All right, but that is, again, it's not a whole number, so not a standing, or it does not form a standing wave. What about 7 here? 6 divided by 7, that is 0 point something, 8 or 9 perhaps. Okay, so again, because there is not a whole number, so D also produces no standing wave. Okay, so we're left only with option A here. Question 19 says, sound waves with frequencies less than 20 Hz cannot be heard by human ear is called what? Is it audible? No, because audibles ranges between 20 to 20,000. This says less than 20. So less than 20, of course, it is called infrasonic. Ultrasonic is higher than 20,000. All of them would be incorrect, so it is only B. Question 20 says, a police car moves at a speed of 25. So this is basically the speed of the source, and emits a sound of frequency of the source. What is the frequency of the sound detected, observed frequency, by a standing observer? That means the speed of the observer is 0 as the police car approaches. That means getting closer. Speed of sound in air is 340. Now we know that whenever there is an approach, let's say between the two, of course, relative motion between the two, and if it is getting closer, the frequency that is observed that is going to be higher than the frequency of the source. But so what is the equation here? Frequency that is observed equal to frequency of the source, speed of sound in air minus speed of the observer, speed of sound in air minus the speed of the source. But this is basically the equation that we use for simple calculation, but you need to know this. If this is the car, let's say, and let's say this is the direction, right? Here's, let's say, the direction of the sound traveling, and this is the observer. So the car is approaching the observer. So in this case, of course, we've learned that if the speed of the car is, or if the car is approaching the observer, you can see that the direction of the motion of the car and the direction of the sound are basically the same. So in this case, of course, V is going to be positive. That is V of the source. But you'll have to go and put that into the equation. That is the frequency of the source, speed of sound in air minus 0, speed of sound in air minus, remember, we do not change this minus, we'll just say plus V of the source. But we know that negative, positive, we are still left with negative, or you could say negative, positive becomes negative, so we still use the same format, you can say. Okay, so the frequency that is observed equal to the frequency of the source, which is 1200 multiplied by 340, okay, 340, and then minus 0. You don't have to write minus 0 now, and then divided by 340 minus the speed of the source, which is 25 here. Okay, let's do the math. All right, we have 1200 multiplied by 340, and then divided by, open bracket, 340 minus 25. The answer is 1295. 1295.2, of course, we can use that as well. So 1295.2, that is the frequency that is observed. Do we have this? Yes, and that is option A here. All right, question 21 says what? Which of the following factors does not change when the sound from a given source becomes louder? All right, it says which one of the following factor does not change? So remember, if or when the sound becomes louder. If it becomes louder, sound intensity, of course, it is going to increase. Amplitude is, of course, it must increase in that case. Relative sound intensity must also increase. But one thing that it doesn't change is the speed of the sound. Remember, speed of the sound does not change here because it is the same medium. And because there's no change in temperature, or at least there's no indication, so it will always stay the same. Okay, question 22 says, the second harmonic of a string instrument has a frequency of 160 Hz. If the speed of waves on the string is 120 meter per second, what is the length of the string here? So remember, we have a string instrument. So the equation for that says second harmonic, don't forget. So this is in harmonic series for string here. So the second harmonic, it is equal to n velocity over 2 times the length. Remember, for a string and for a pipe that is open at both ends, it is 2L. If it is a pipe that is open at one end, it would have been 4L here. But since it is string, so 2L. Now, all you have to do is just find the length of the string here. So the frequency that we have, it is 160 Hertz. Let's not write the hertz now. So second harmonic, so n is 2, multiplied by the speed of sound, or the speed of the wave on the string is 120 meter per second, and then times or divided by 2 times the length of the string here. This 2 and 2 cancel out, so we can say the length of the string, it is 120 divided by 160. These 2 cancel out. 12 divided by 16, that is clearly 3 over 4. That is 0.75. You don't have to do the mental math, by the way. You have your calculator, always use that. So the length of the string is now 0.75. All right, the next question here says, what is the intensity of a sound or of sound waves emitted by a radio at a distance of? So we have a distance. If the power generated from the radio is 30 watts, so here's the power. It says, assume that the sound waves are spherical. All right, so the intensity. We know that this is for sound. So intensity, question 23, intensity, it is equal to power divided by the area, but spherical area. So power divided by 4 pi r squared. Okay, now in this case, of course, the power is 30 watts divided by 4 pi times the distance is 5 meters, so 5 squared in this case here. So let's do the math. 30 divided by, open bracket, 4 pi multiplied by 5 squared, close bracket, and that is going to be 0.0954. We could say 0.09, 0.095, because the digit after that, it is 4. So if we take 2 digits, it's going to stay as 0.0995. So do we have, that is basically the intensity, which is watt per meter squared. Okay, but if you look at the option here, of course, this is the closest one. And you saw the digit after 5, it was 4, so it cannot be rounded up. But this may be due to an accident. Okay, so now for question 24 says, what is the magnitude of a magnetic force on an electron when it enters a magnetic field at right angle or at a right angle? Remember, this one says the magnitude of a magnetic force. So do not choose, for example, this negative, because say this is an electron, so it should be negative. No, the magnitude of the magnetic force, it is equal to what? It is equal to QVB here, because we're only concerned with the magnitude, so that is going to be option A. All right, question 25. It says, what is the magnitude of a magnetic field strength? So B, the magnitude of B, all right, the magnitude, this is 25. So what is B? Okay, strength at a distance of, so we have a distance, okay, distance of 0.1 meter, you can call it radius as well, from a straight wire carrying current. So if there is a straight wire here, this distance, of course, will be the radius as well. if there is a current occurring, a current of 15 ampere. So the current that is passing through the wire is 15 ampere. Now the magnetic field for a wire, you know that we have a magnetic field for a straight wire, for a coil, and for a solenoid as well. For a straight wire, it is mu naught I current divided by what? Divided by 2 pi d. Okay, mu naught is given, which is 4 pi times 10 to the power negative 7, multiplied by the current, which is 15, divided by 2 pi, multiplied by the distance, which is 0.1 meter. All right, let's do the math and see what it is. That is 4 pi's multiplied by 10 to the power negative 7, here's negative 7, multiplied by 15, equal to, and then divided. You always press equal so that it makes it easier for you. Divided by, now you can open bracket 2 pi times 0.1. And of course the answer is 3 times 10 to the power negative 5 Tesla, because it is a magnetic field. Do we have this? Yes, that is option C. All right. Question 26 says, the magnitude of the magnetic field strength at the center of a circular coil. Now this time we have a magnetic field strength at the center of a coil this time, but it says varies inversely. Okay, with what? Now in order to do this correctly, you can always write the equation here. Okay, now in order to do this correctly here, write the equation of a magnetic field strength for a coil. That is mu naught Ni over what? Over 2R. Okay, so now anything above the fraction, that means it is directly proportional. By increasing those factors or values, B would increase. But anything below the fraction, that means inversely proportional, which means that if you increase this, B, of course, is going to decrease. So this is called inversely proportional. Okay, so now let's go and analyze the option here. It says it varies inversely with the number of turns. No, because the number of turns is directly proportional. The intensity of the current. No, because it is, again, directly proportional. With the radius of the coil, is it inversely proportional with the radius of the coil? Yes, because that is below the fraction, and it cannot be all of them. Okay, so that is option C. Question 27 says, in which of the following is the direction of the magnetic force on a proton? So proton is a positive charge. Don't forget, that is the palm of your hand. Moving in a magnetic field is into the page. Into the page, that means F magnetic must be in the direction of Z negative. Now, of course, it would have been best if I could show you how you can use the right-hand rule, but there's always a way, and there's a very easy way. We can make a table, of course. That table is going to be for both B, magnetic field strength, V, and then, of course, we can say the force as well. So here's B and V, and this is magnetic force. But look, the magnetic force here says it is into the page, so it has to be in negative Z direction. Now, let me tell you this. So each one of these, in order, for example, you know that the angle between each one of these is basically, normally, it is at right angle to one another. So, for example, if this is B, let's say this is V, this is going to be the force here. Or it doesn't matter which one you call it, BV, or the force in here. So, but the angle between each one of these is basically 90 degrees here. Don't forget this. So, here the study tip, okay? So if any of these, for example, any of these are in the same axis here, immediately is going to be incorrect. For example, if one of them is, now we know that it tells you the force is into the page in negative Z axis, or the axis is Z direction or Z axis here. So if any, or B or V, if it is in Z axis, whether if it is positive or negative, it is immediately going to be incorrect, because we cannot have two things on the same direction, whether they are same direction or opposite direction here. It cannot be on the same axis. So that'll be incorrect, because it has to be on separate angles here. Now you will see what I mean by this. The first option that we have, you can see that the magnetic field strength is pointing outward, so that is out of the page. Out of the page, that means Z positive. You see? we have if magnetic field is on z-axis, can the magnetic force be on z-axis as well? No. So from this point on, we can say option A is incorrect, but let me tell you why. So V here, it is basically towards or to your right, so we can say it is towards the negative x-axis. So if you use your right-hand rule now, try to point your fingers upward to the ceiling, right, to the top, and then your thumb to your left, basically, that is towards x negative. You'll see that your palm is basically facing in front of you, and of course that is basically going to be y positive. But the question says the magnetic force, it is into the page, so option A, it is going to be incorrect. What about option B? So we could have said incorrect from the beginning because magnetic field was on z-axis as well, so we cannot have two things on the same axis. So what about option B? The magnetic field is downward negative or y negative, and then the velocity is basically x negative. So these are in opposite, on different or separate axes, but let's see if it is correct. Your fingers should be pointing downward, okay? So in this case, of course, you can say, I don't know how would you do that, but that is basically your fingers basically pointing towards your back. All right, and then in that case, of course, but if you look, for example, the V direction, right, it is basically pointing to your left still, that is x negative. Now you can see that your palm is basically facing upward. Facing upward, that is basically z positive, not negative. So this is also incorrect in here. So option B is also incorrect. What about option C here? We have the magnetic field that is into the page. Into the page, that means z negative. Can we have magnetic field on z-axis and then magnetic force on z-axis? No. So we can say immediately C is incorrect. What about option D? The magnetic field is towards x positive, that is to your right, and then the velocity is y positive, that is, you can see that, and then pointing ahead of you, you can say. And then what about the magnetic force? Use your right hand rule. Full finger pointing right, your thumb pointing north or in front of you. You can see that your palm is basically now must face downward. Facing downward, that means it is into the page or z negative. So now you can see that option D is the correct one. Okay, question 28 now. I hope that was clear. If not, try to listen to this video like at least a few times until it makes sense to you. And you can always rely on the table to tell which one is right or wrong here. Okay, now as for question 28 says, a current of intensity 15 ampere or amperes is passing through a wire that is perpendicular to a uniform magnetic field. Question 28. We have a current of 15 amperes passing through a wire perpendicular to a uniform magnetic field. A force per unit length. Remember, force per unit length. That means F over L is equal to 0.112 Newton per meter is exerted on the wire. What is the magnitude of the magnetic field strength? What is B? Since it says a wire, so remember, magnetic force for a wire, we know that. Magnetic force for a wire is equal to BIL here. But since we have force per unit length, we could divide both sides by L or bring this L here. It becomes magnetic force over L, that is B times I. All you have to do is just plug in the numbers now. Magnetic force per unit length is 0.12 equal to B is required. The current is 15. Now B, it is equal to 0.12 divided by 15. Let's see what that equal to. 0.12 divided by 15. The answer is going to be 8 times 10 to the power negative 3. And that is Tesla because it is a magnetic field. Let's see if we have this one. 8 times 10 to the power negative 3. That is option C. Okay. Question 29 says calculate the power lost. Now, whenever it comes to power loss, it's easy because the equation for power lost, this is obviously known, okay, or you can say easy to do the calculation. says of a wire of resistance, so this is the resistance, traversed by a current, so this is the current here. What is it equal to? We know that power loss that is equal to, this is question 29. Power loss that is equal to current squared times the radius. The current that we have, it is 50, so 50 squared times the resistance, not the radius. The resistance is 120 ohms. So let's do the math. 50 squared, all right, multiplied by 120. The answer is 300,000. 300,000, that is power, so it is in watt. So of course, can I write 300 instead of this 1,000, call it kilowatts? Yes. And this is kilo because in all the options I had kilo. This is why I've converted this to a kilo. So which one is 300 kilo? That is option D. Okay. Question 30 says the electric current grows in a circuit from 0.0 ampere to 10 ampere. So we can call this one I1 and this is I2 here during a time of 0.1 second. What is the induced EMF? Within the circuit of the coefficient of self-induction L, it is 0.02 Henry. Okay, let's solve this one too. That is 30. EMF, because we have a change in current, so we'll use this equation. Delta I over delta T. So EMF induced negative 0.02 times change in current. So I2, 10 minus I1, which is 0, divided by 0.1 here. That is going to be 10 divided by 0.1. That is 100. 100 times negative 0.02. That is going to be negative 2 volt here. So EMF induced is negative 2. Do we have negative 2? Yes, that is option B. All right, next one here is 30, says, which of the following is correct? Now at this point here, or some of these kind of questions will be a little bit annoying to some of the students, but you guys don't worry. Let me tell you how you could do this. If you look at the options, in each one of these, we have volts in here. So of course, and then multiply by the second. So of course, where do we have these stuff? Whenever we have EMF, for example, and delta T's, where U, for example, this is normally measured in voltage, and this is in second, but once you cross multiply, of course, you can get volt second. But what are the equations that we have, right? Now, so think about the equations. We have EMF, and of course, there is delta T as well. How about Faraday's law? Of course, we have negative N, change in flux, where you can say AB cosine theta, or change in AB cosine theta. So this EMF, it is measured in volt. It is equal to number of turns, that is, you could say unitless, or just number of turns, so nothing there. The area is measured in meter squared. Magnetic field strength measured in Tesla. Cosine theta, that is basically, we can say no unit for this, that is in degrees, we don't count that. Delta T is measured in seconds. So if you cross multiply or make Tesla the subject, we'll get volt second, it is equal to meter squared Tesla. So make Tesla the subject, that is volt second divided by meter squared. So this is what Tesla is equal to here. So do we have this in the options? Yes, and that is option B here, we could say. Okay, that is volt second divided by meter squared. Okay, what about 32? It says, when a motor is operating, the faster the coil turns, the magnitude of what? We know that the faster the coil turns, of course, there is the more opposition, of course. If there is more opposition, we can say the back EMF increases, but let's check the other options here. B says, the current of the coil increases. No, it does not increase. The back EMF decreases. No, because there's faster rotation, so it must increase. D says, the current of the coil stays the same. That is also incorrect. So, of course, that is option A. All right, next. We have 33 says, which of the following equation is correct to calculate the magnitude of the maximum EMF for a generator? Now remember, for a generator, we have this equation. So we can say EMF induced, that is equal to NAB omega sine omega t. But when we talk about maximum, that means this sine omega t must equal to 1. If it is equal to 1, then of course we can call this one maximum EMF, because any other, where the value for this at any other angle is going to be less than this value. So we can say this is going to be maximum here. That is NAB omega. Which one is NAB omega? That is option C here. All right, question 34 says, in the circuit shown, what is the total potential difference? It has to be difference. VT between A and B. This is perhaps on me. Okay, the translation. So in this case, of course, since we have this is AB basically, so because this is a series circuit, so we can say total potential difference, we'll use the radical of, we can say VR squared plus VL minus VC, the whole thing squared. So VR is basically, what is VR? That is 8, so 8 squared plus VL is basically 10 minus VC, which is 4, the whole thing squared. If you do some math in here, by the way, you have to use your calculators, don't do mental math. 8, that is squared, that is 64, plus 10 minus 4, that is 6, 6 squared, that is 36, you can say. So 64 and 36, that is 100, and the square root of 100, it is 10, so 10 what? 10 volt. But you don't do the mental math, by the way. Use your calculator, it is way safer. So of course now it is going to be option C. All right. Question 35 says, a coil of negligible resistance with a coefficient of self-induction of 0.05 Henry is connected to a source of 50 Hertz. What is the inductive impedance? Now, whenever it says inductive impedance, that is basically, you could say XL here. This is question 35. So what is XL? We know that XL, it is equal to omega L. Since we don't have omega directly, omega is equal to 2 pi F times L here. 2 pi times the frequency is 50, and coefficient of self-induction, it is 0.05 Henry. So let's do the math. 2 pi multiplied by 50 Hertz multiplied by 0.05. The answer is 5 pi, or you could say 15.7. And of course, this 0 can be rounded up, 15.71. That is ohms. This is XL. Do we have this? 15.7, of course we have option C. Question 36 says, a resonance circuit is made up of an inductive coil and a variable capacitor. So the capacitor can change. If the capacitance of the capacitor lowered or changed from 800 microfarad to 200 microfarad, by what factor does the resonating frequency change? Okay. So now we can say, because we have 2 volleys of this, of course we can say this is a resonating circuit, so we can say the F2 over F1. But what is the frequency of the resonating circuit it is equal to? It is equal to 1 over 2 pi, the radical of L times C. Again, for F1 is the same thing. 1 over 2 pi, the radical of L times C. So we can call this one C2 and call this one C1. The rest of the volleys are not changing, so it is constant. Since it is constant, of course, each one of these, of course, they can cancel out. One, we don't have to do this, but these are all cancel out. And of course, even with the L here, but let me do one step further here. So now this one, of course, or this factor comes down because it's under the fraction. This one goes up. So in this case, F2 over F1, it is equal to, we can say, let's use one radical for both, as LC1 over LC2. L and L, of course, both cancel out again. So now we can say F2 over F1, it is equal to the radical of C1 over C2. But what is C1 here? C1, it is, or the volley for the capacitance, it was 800 microfarad, and then divided by 200 microfarad. You might say, how about converting micro? Well, in this case, whether you convert micro, for example, to 10 to the power negative 6 or not, it makes no difference because these are both microfarad, they cancel out. Even if you say 10 to the power negative 6 farad, 10 to the power negative 6 farad, Again, these two will both, again, cancel out, so no need to at this point. So in this case, of course, 800 divided by 200, that is basically, you could, of course, simplify this. That is simply 2. So F2 over F1, it is not 2 first, I mean, my bad. First of all, that is going to be, or you could simplify this, it is going to be 4 over 1. But if you take the square root for this one, F2 over F1, it is equal to 2 over 1. We'll write 2 over 1 if they want the ratio. But here, since they're asking for a factor here, so it is totally fine if we just say F2 over F1, it is only equal to 2 in this case, and that is going to be option C. But once again, if they ask for the ratio, you have to keep 2 over 1, because otherwise it would be incorrect. Okay. What about question 37 says, what is XC equal to? That is the capacitive impedance. We know that capacitive impedance, or XC, that is equal to 1 over, that is 37 now. XC, it is equal to 1 over omega C. Do we have 1 over omega C now? So we'll have to simplify this further. Instead of omega, we have 2 pi f multiplied by c. Do we have this? Yes, and that is option D. So this is the capacitive impedance. Question 38 says a step-up transformer increases the potential difference from 120 to 2400. All right, so this is 38. V1 is 120. V2 is 2400. These are in volts. If the primary has 75 turns, so this is N1, 75 turns. What is the number of turns in the secondary, you could say, huh? How many turns must the secondary have? So we have this equation, N2 over N1, that is equal to V2 over V1. All right, let's plug in the numbers. So N2 is required, N1 is 75, equal to V2 is 2400, V1 is 120. So you could simplify those, of course. 24 by 12, that is basically 2, that is going to be 20, 20 times 75. You don't have to go through this one, just cross multiply. So N2, it is equal to 75 times whatever the answer to this fraction. Let me just rewrite it. 2400 divided by 120. So you do the math, of course, you'll find the answer. Let's find it out. So we have, let's do the fraction first. 2400 divided by 120 is equal to 20 times 75. That is 1,500 turns, of course. That is N2. Do we have this? Yes, and that is option B. Question 39 says, what is the necessary condition for the path length difference between two light waves to interfere destructively? Now, we know that if, in order for two waves to interfere destructively, the phase difference between the two must be 180 degrees. And how do we get 180 degrees? There must always be a half wavelength extra, you can say. But look at the options. It's a little bit, you have to be careful with that. It says an integral number of a wavelength. No, it cannot be that. Can we say any wavelength path difference? No. What about an odd number of wavelength? It cannot be, for example, like 1 wavelength, 3 wavelength. No, these are whole wavelengths. So again, these are all constructive. What about option C? Says an odd integral number of half of the wavelength. And yes, of course, that could be, for example, any number with a half a wavelength. So in that case, of course, that would lead to, for example, let's say 1 over 2 plus m, let's say, wavelength. So that could be any number here. But as a result of this, what do you get? You get, for example, 1 over 2 wavelength, or let's say 3 over 2 wavelength, or 5 over 2 wavelength, or it could be 7 over 2, 9 over 2, 11 over 2, and so forth, of course. So that is option C. D says an even integral number. No, that is incorrect, because if it is even, of course, at some point you get a full number. All right, or a full whole number, you could say. Question 4T says, what is the period of a 3.5 meter long pendulum at the North Pole of the Earth? So remember the equation of a pendulum. So all you have to do, just apply the equation. That'll be it. Question 40. The period of a pendulum, it is equal to 2 pi, the radical of length of a pendulum divided by gravitational acceleration. So again, 2 pi multiplied by the length of the pendulum is 3.5 meters divided by gravitational acceleration. But look, this one is, don't write 9.81 because this is given here. So 3.5 divided by 9.832. If it was not given, of course, then we would have used 9.81. But since it is given, it is a condition and you need to use that value only. So again, we could say 2 pi multiplied by the radical of, you could use this one, by the way, the same that I'm doing here. I have other options, but I'm trying to use the same thing that you could use or benefit from this, 832. So once you do this, that is 3.748. We can say 3.75 by rounding. That is going to be the period which is in second here. Do we have this 3.75? Yes, and that is option A. Okay. Question 41 says, a diffraction grating with 4525 lines per centimeter is illuminated by direct sunlight. The first order solar spectrum is spread out on a white screen hanging on a wall that is opposite to the grating. At what angle does the first order maxima of red light with a wavelength of 655 nanometer appears? So what do we have? The first order here. And look, we have diffraction grating. So first of all, you will have to find d, the distance between two slits, let's say, and then after that, you could do the math in here. But let me do this one here. So the question says at what angle, so you'll have to find sine theta. This is the equation first. Since it is first order solar, that is for the bright, you could say constructive. So d sine theta, it is equal to m lambda. You know this one. So we're trying to find this angle right here. But first of all, let me find the slit separation here. And that is, of course, we could say d, it is equal to, let me write it here, 1 over the number of lines per unit length in here. The length goes up, so this is in centimeter here. So let's see what that equal to. 1 over the number of line is 4525. And then times, if we convert centimeter to meter, you multiply by 10 to the power negative 2. So let's see. 1 divided by 4525. I'll do the times later. Okay, and then multiply. The answer multiply by 10 to the power negative 2. The answer is going to be 2.209 times 10 to the power negative 6. Can I say 2.21? Yes, 2.21 times 10 to the power negative 6. That is going to be basically, that is the distance between two slits, which is going to be in meter. Now, since you found the distance, of course, you could find the answer now. So we can say this, says find the angle here. So in one step, I could do this one first of all. I can say sine theta, it is equal to m lambda over d. But if we're trying to find the, let's just do this one, like take each step at a time here. Says the first order, so m is 1. The wavelength for red light, it is 655 nano, that is 10 to the power negative 9, divided by the distance here, which is 2.21 times 10 to the power negative 6. Let's find this one here. And then after that, once you do this, of course, we want the angle here. So we'll say theta, it is equal to sine inverse of the answer, whatever the answer is. Of course, you will find the angle. All right, let's do that now. So we have 655 times 10 to the power negative 9. That is this divided by, bracket, 2.21 times 10 to the power negative 6. So the answer is basically, we can say 0.2963. If we can take 3 digit here, it's going to be 2.2963. 0.96. 0.296. Let's just read 296. Okay, now take the sine inverse of that. Let's just say sine inverse of the answer. Sorry, sine inverse of the answer. This will give us perhaps even more accurate answer now. So it is going to be 17.2 here. So the angle is 17.2 degrees here. Okay, that is the angle. We have 17.2. 2,4, of course, you could go further, and that is option C. All right, question 42 says, which property of laser causes coherent light to be emitted? Which property of laser causes coherent light to be emitted here? Now, what do we mean by coherent light? So, for example, here is a wave, let's say, going into or colliding with an atom, and of course, two same, let's say, or two waves would come out. But remember, these two waves are exactly the same here. They have basically the same wavelength, they have the same phase difference and all that. So this is basically called coherent here. But what causes this coherence, of course, or what is it exactly called? For example, when we have two same wavelength, same frequency, same amplitude, you can call this one coherent. Okay, but what causes this? Is it the different intensity? No. Is it light amplification? No. Is it stimulated emission? Yes. Okay, what about monochromaticity? That is incorrect. So it is stimulated emission. Question 43 says radiation emitted from a human skin reaches its peak at lambda, or wavelength, that is 940 micro, that is 10 to the power negative 6. How much energy in electron volt is carried by one quantum of this radiation? And Planck's constant is given here. We know that, of course, the energy, that is question 43, E it is equal to hf. But since the frequency is not given, we know that here. So speed of light, frequency times the wavelength. Frequency equal to speed over the wavelength. So we can substitute that. E, that is equal to Planck's constant, C over the wavelength. So now all you have to do is just do the math. Let's do it here. Planck's constant, that is 6.63 times 10 to the power negative 34 multiplied by speed of light, that is 10 to the 3 times 10 to the power 8, divided by the wavelength, which is 940 micro, that is negative 6. Let's do the math and see what is the energy. But you have to be careful here. The energy that we get in here, that is going to be in joules. You have to convert that into electron volt. So 6.63 times 10 to the power negative 34 multiplied by 3 times 10 to the power 8. You can press equal, then divided by 940 micro, which is 10 to the power negative 6. The answer is 2.11, or you can say 11590 or whatever. By rounding it up, of course, we can say 2.116 if we want to. But that is in joules, we can say. So we can say let's just call it 116 if you want to. That's not how you read a digit, but still. 2.1111, we could say 6 here. That is going to be joule. But how do we convert joule to electron volt? We simply divide by 1.6 times 10 to the power negative 19. And that's it. We will be converting joule to EV. Okay, electron volt. So let's divide that with 1.6 times 10 to the power negative 19. Let's see what that equals to. Oops, I've done something incorrect. Yes, that's the bracket in here. Let's use this one to get a correct answer here. So that is 1.322 times 10 to the power negative 3 electron volts. So we could say 1.3 here. 1.32, let's say. 1.32 times 10 to the power negative 3 electron volt. That is basically the energy. Do we have this? No, perhaps I've done something incorrect. No, wait, let me see. 1.32, yes, that is option A. Okay, question 44 says, what is another term for quantum of light? Quantum is a pocket of light, and of course another term for that, it is photon. But can we say it's black body radiation? No. Energy level? No. Frequency? No. It is a photon. Question 45 says, an electron in a hydrogen atom drops from energy level E4, which is negative 0.85 electron volt, to energy level of E2, negative 3.4 eV. What is the energy of this emitted photon here? Okay, so let's do this one too. That is question 45. Remember, there is basically an electron dropping from E4 to E2 here. Of course, while it is dropping, it has a higher energy here, is going to drop to lower energies. Of course, it's going to emit the energy. What is the change in that energy between E4 and E2? So, of course, change in energy, or you can say the energy here, let's just call it the energy. That'll be the difference between the two. E1, which in this case is basically E4, we could say, minus E2. So it's going to be negative 0. Or is E4 here? 0.85, and then minus, and then there is another minus, you could say. So it's going to be positive. So let's just write plus. This minus will be positive. E2 is also, let me just write this one. Minus 3.4. These are in EV here. So of course it's going to be negative 0.85 plus 3.4. So let's do the math and see what that equal to. Negative 8.5, sorry, negative 0.85 plus 3.4. That is going to be 2.55 electron volt. That is positive electron volt. Okay, do we have that? We should. That is option A. All right, now look at question 46. By the way, this diagram is not given, but I've attached to this so that you can see the difference. It says, what type of spectrum is used to identify the elements in the atmosphere of stars here? Of course, you've learned by now there are, like for example, this is called emission spectrum. You can see the background is all dark, and only we have those colors that are emitted here. But if you look at the lower one, you can see the background is colorful, and then we have some dark lines. The dark lines, it means that there are certain frequencies that are absorbed. This is why they're missing, for example, as a color here. So of course, this is called emission spectrum. This is called absorption. The lower one is called absorption spectrum. So the question says, which type of spectrum is used to identify the elements in the atmosphere of star? Of course, is it the visible spectrum? No. Is it a continuous spectrum? No. Is it an emission spectrum? No. It is an absorption spectrum that is used to identify the elements in the atmospheres of stars. Question 47 says, an electric field is oriented as shown in the figure. In which direction do the electrons and holes? Electrons basically are negative, holes are positive or represent positive charges, move within the field in here. So of course, if you have a field, you can always do this. Fields are moving, let's say, in the direction of a positive, let's say, electric force on a positive charge or whatever, test charge here. So if it is, we can say this side is positive, the other side is negative. If you do this one, always these lines are coming out from positive to, let's say, towards the negative. So if you have two charges now, one of them is negative, the other one is positive. We know that negative would be pulled towards the positive. Positive would be repelled or move away from one another. So if we do this one more time, we can say that the negative charge is going to move to the left. The positive charge will move to the right in here. So which one of these is correct? Electrons move to the left. Holes move to the right. So this is correct. But let's analyze or check the other option. Holes move to the left. That is incorrect. Electrons move to the right. No. Holes move to the left and electrons move to the left. No, they cannot move to the same direction. Holes move to the right, electrons move to the right. That is incorrect once again because they can all move in the same direction here. Okay, So that is option A. That was 48 says, in which of the following cases can a superconducting material not be used? We know that superconducting materials are good conductors. This is a reason why we call them superconducting, because they don't lose energy. If they don't lose energy, that means there is no resistance. If there is no resistance, there is no heating effect, you can say. So the first one says, in heating devices and ovens. Can it be used in heating devices and ovens? Of course not. Okay, because if they don't lose any energy, there will be no heating effect. So they cannot be used in heating devices and ovens. But can they be used in transferring energy with no loss? Yes, because they don't have any resistance. So not to be. In the storage of electrical devices, yes. If they're not losing any energy, of course, it would be perfect in that case. In the magnetic levitation, so they can be used in that as, you can say as, because these are superconducting materials, so of course they can provide a very good magnetic field. They can also, as long as there is no energy lost, so they can retain that, you can say. What about 49? So that was option A, of course. 49 says a diode is connected to a source of alternating current. So we have an alternating current, you know that. What is a diode? Is basically, this is, you know, what is a diode? It allows the current to go in forward direction only. So if we have alternating current, we have positive and negative sides. So if we connect a diode to this, it only allow the positive part to go through. When the current reverses, for example, comes from the negative side to positive, then let's say this is positive, the other side is negative, it cannot go the other direction or in reverse. So the question says, the current in the source that fluctuates between, so we have a current that fluctuates between what and what? Fluctuates between negative 1 milliampere, so this is in milliamperes, this is, let's start with this one here. So we can say this is negative 1 milliampere up to positive 1 milliampere. This is basically the values of current. So we have positive and negative since it is alternating. This is the value of the current. It says, what will be the range of the rectified current? Now, after this passes through a diode, of course, let's say, if we have a diode, it only allows, let me do this one last. It only allows the positive part to pass through. Once the current is reversed, it does not allow it to go. So in this case, of course, what will be the resultant of this alternating current now? We will still have the positive part, but what happens to the negative part? Once the current is reversed, the diode does not allow the current to go. So now, what is the value of the current that is left now? This is 0 clearly, so only keeps the positive part, so this is 1 milliampere. What about the negative side? There is no negative side here. So we can say this rectifier, this rectified current, it is in a range of 0 to only positive 1 milliampere. There is no negative part in this case, so it is only from 0 to that positive value, which is to positive 1. So what are the options here? It says from negative 1 to positive 1. No, as soon as you see negative, cross it out. From 0 to 1, yes, this is correct, because there is basically from 0 all the way to 1. What about option C? Said as long as you see negative, cross it out, because there's a diode. From 0 to 2, that is incorrect, because we cannot create, like, let's say, alternating currents here. This part would be cut off. It's not like this part would be added to the other part. No, it's just going to be cut off. So that is still between 0 to 1 milliampere only. So that is option B. The last question that we have says, the symbol L in the equation, L equal to I times moment of inertia times angular speed is equal to what? Or what is it equal to? Is it the moment of inertia? No, because moment of inertia is I. Is it the rotational kinetic energy? That is no. Is it the torque? No. Is it, if these are not that, of course, is it the angular momentum? Yes. So, of course, we can say that is option D. That is the end of these questions. I hope you found it beneficial. Inshallah, there will be more videos like this. So stay tuned. Assalamu alaikum wa rahmatullah.